Hi everybody and welcome. Today we're going to be talking about right triangles and some theorems that we can apply to these right triangles. So to start off, our definition is actually just going to define some of the parts of those right triangles. And just as a quick refresher, this is a triangle with one 90-degree angle. And a couple pieces of, we'll say, the anatomy, or just the things that make up these triangles here. So if you draw one, of course we're going to see one right angle, but what we're also going to see is a leg and a second leg. And those are the pieces that are directly next to that right angle. And then the third piece, another vocab word for us, is the hypotenuse. And that's just a fancy way of saying the longest side. And a final thing, and I'll draw this in yellow, a reminder to a unit that we've already done. If you have a segment that intersects at a right angle, we call that a altitude. So drawn in yellow there is an altitude. So some vocab words to refresh, kind of set the stage for some of the things that we're going to be doing today. So we can keep moving down here. Next, here, maybe I can put this on the top would be best. So we're going to be looking at some similar triangles. And the first piece of information that's important about altitudes and right triangles is that if you draw one, it actually forms two more triangles, and those triangles are actually similar to the original one. So let's say our original one is in yellow. So that's our large one here. It's around the outside. It forms two new ones, and each of these are similar. So this green one is also similar, and the red one is also similar. When we write our statements here, we have to be careful to make sure that we're matching up the things. So if we're naming the three similar triangles here, it's important that we do it in order. So if we go from triangle ABC, we went from A to B, B to C, so we went from our smallest side to our hypotenuse. We have to make sure that on our next triangle, we also go from the smallest side to the hypotenuse as well. So here, we want to do the same thing. So we're going to go from our smallest side and then to the hypotenuse next. So we're going to go from D to B, and then from B to A. I should write that up here, D, B, A. And again, each of these, we carefully made sure that we matched smallest side to hypotenuse. We followed the same order, and that's why we're allowed to do that. So now it's your job to actually go through and, let's do this again, ABC, and do the same thing, except this time for our green triangle, and get that matched up for a similarity statement. So that's our kind of second piece of information here about similar triangles, is matching them up, and just like we've been doing so carefully many times this semester, making sure that they match up and naming those sides in the correct order. Next, we're moving on to something called the geometric mean. So a totally new concept here. And the geometric mean is basically you have two numbers, and the geometric mean of them is x. And the way that you solve for it is just a formula. Don't need to read into this too much. The geometric mean of A and B is you plug in for A, and you also plug in for B. And when you do that, you'll be able to solve for x, because x is the only unknown. So for example here, with our geometric mean, so we don't know it, so we always start off like this. We're trying to find the geometric mean of 3 and of 10. So if this looks like a lot, but it's actually not too bad once we get started working, we still cross multiply. So x times x gosh, I am having a hard time writing today. X times x, or x squared on one side, and then our green on the other side is 3 times 10, or 30. So we get x squared equals 30, and then we can finish solving this, and we'll solve for x. So x is the root of 30, and that is the geometric mean of 3 and 10, is the root of 30. And then we can keep doing that for the second one. Again, you want to set up a similar proportion, and then go through and solve. And it's even okay to write this as a decimal here. So if we had, for example, the square root of 30, we could punch that into our calculator and get an answer of 5.4. Actually, we should round that up to 5.5. All right, so that is our first kind of page of notes here. Now, the second thing that we need to do is kind of apply these things even further. So if we take a look here, we'll get a little bit closer. We can use the geometric mean to solve for things in right triangles. So the theorem that we are being introduced to, and we want to add this to our list, definitely in our notes here. In a right triangle, the length of the altitude from the right angle to the hypotenuse is the geometric mean of the lengths of the two segments that hypotenuse is basically split up into. So a reminder, hypotenuse is our longest side. In green here, this is our altitude, and it's saying the geometric mean. So the answer to the geometric mean, remember, that was the x term that we set up like this, is the two numbers we see here. So if we take the geometric mean of 6 and 10, that's going to give us x. So it's our job to go through here to cross multiply and solve. So we'll get x squared equals 60, or we can say that x equals the square root of 60. So if we take the square root of 60, we'll get an answer of 7.7. And that's how we would solve questions just like that. Well, that's not the only theorem with our right triangles here. Additionally, in a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into two segments. Each leg, so again, leg, remember those are the other sides of the triangle, is the geometric mean of the hypotenuse, and the segment of the hypotenuse that is adjacent to that leg, or next to that leg. So it's telling us that the leg is the geometric mean. So if you're looking at setting up an example here, let's go through and just solve number 5. The leg here, x, that is the geometric mean. So if we're setting up a proportion, we would start off by putting the answer to the geometric mean here. Now the other two segments that we need are, let's go back to our definition here. Let's make sure we're reading this together. So it's the geometric mean of the hypotenuse and the segment of the hypotenuse that is adjacent to the leg. Well, this is our whole hypotenuse, so we'll put that as one of our answers. So 24 plus 2, or 26. And then the segment of it that is closest to the leg, or adjacent to the leg, well, that's the segment there, that's 2. So if we're solving for x in this case, we would cross multiply and then divide. So we would get 52 equals x squared. We could take the root of both of those and get an answer. Gosh, hopefully it's not breaking on me here. Of x equals the root of 52, or if we take the root of 52, we'll get 7.2. So that's how we would solve. And that's going to be your job setting up for the bottom, is making sure that we're doing a similar proportion. So again, telling us that the leg of the triangle, that is, and again, the leg, that's going to be the full side of the length there. And we can solve just like we did for number 5 for 6, 7, and 8. Let's go back and answer these questions. So the hypotenuse, the segment of the hypotenuse that is adjacent to leg AB, or the black one here, is 2. And the segment of the hypotenuse that is adjacent to leg, we'll make it squiggly, AC, is 24. That's the other piece. So regardless of how you set this up, you have the information to set up those proportions, and that's kind of what you're going to be working through when you finish up these questions. So as always, everybody, thanks for tuning in. That's kind of our video here, so make sure, again, a couple new theorems today, some new vocab words to freshen up on. And as always, questions, reach out, book an appointment, do any of those things, and I'll see you in team.